Imagine waking up to a sudden, silent apocalypse. If every carbon atom on Earth instantly vanished, the planet would be unrecognizable in seconds. Every tree, every animal, and every single human being would rapidly dissolve into formless dust. The biological world would simply cease to exist. Here is the bizarre cosmic paradox. Despite our absolute reliance on it, the Big Bang produced 0 carbon atoms. The universe's original recipe was essentially nothing but hydrogen and helium. Humanity's existence relies entirely on a mystery element missing from the dawn of time. To find where we actually came from, we have to look much later in the timeline. Millions of years after the Big Bang, massive stars lit up the darkness. Deep inside these giants, crushing pressure and intense heat functioned as nuclear factories, eventually fusing lighter atoms together to forge carbon. When those ancient stars died, they tore themselves apart in massive supernova explosions, scattering this newly created material across the empty void of space. Over billions of years, those drifting clouds of stardust pulled together. They slowly coalesce to form planets, oceans, and eventually the ground we walk on. Consider the physical reality of your own body. Every single carbon atom inside you is physically older than the Earth itself. So when this stardust finally settled on our planet, why did nature select carbon out of the entire periodic table to build biology? The answer lies in its 4 available bonding sites. These allow a single carbon atom to link with almost any other atom, creating millions of stable shapes. When these connections fold, they provide the structural stability required for DNA. That same microscopic geometry scales up. Those bonds form proteins, which build living cells, which grow into the plants outside your window, and eventually, humans. Carbon operates as the foundational architecture upon which all biological life is constructed. Carbon's versatility extends to the minerals beneath our feet. Look at a common pencil, something you can snap with 2 fingers, and compare it to a diamond, the hardest material known to science. Chemically, they are identical. The graphite in that pencil and the raw, translucent diamond resting in the rock are made of the exact same atoms. The only difference is their internal geometry. In diamonds, carbon atoms lock in a rigid, 3-dimensional grid, capable of cutting steel. In graphite, they form flat sheets that gently slide past each other, which is why it rubs onto paper. Carbon's power lies in its capacity to disguise and reorganize itself through simple shifts in its atomic arrangement. For millions of years, the Earth managed this element through a natural cycle, moving carbon seamlessly between oceans, rocks, and the atmosphere. Humanity disrupted that rhythm. We began digging up millions of years' worth of deeply buried pressurized carbon in the form of fossil fuels and burning it for energy. Flooding the air with excess carbon dioxide created a thermal blanket. It traps the sun's heat, driving the global climate change we see today. We are now facing a paradox. The same element that creates all earthly biology has become a primary threat to our planetary survival. To address the thermal blanket we've created, we are beginning to look at carbon not just as a waste product, but as a resource to be managed. Engineers are developing carbon capture systems. These technologies actively vacuum the element directly out of the sky, separating the CO2 and pumping it safely underground to stabilize the atmosphere. Beyond cleanup, we are manipulating carbon on an atomic level. By isolating a single atomic layer of graphite, we've created graphene, a material with properties we are only beginning to understand. These technologies represent a shift in how we handle the element, moving from a history of simple combustion toward a future of precise molecular engineering. When we shape these isolated carbon structures into nanotubes, we create materials that are hundreds of times stronger than steel, yet nearly weightless. We are already using these engineered carbon fibers to build the next generation of aerospace designs, electric vehicles, and the deep space probes exploring our solar system. It is a staggering cosmic journey. An element born in the cores of dying stars, drifted across the void to build your DNA, was buried to form diamonds, and is now being engineered to solve our modern challenges. Take a breath. Every heartbeat you feel and every thought you have right now is physically powered by those same ancient atoms. If carbon can shapeshift from stardust to the hull of a spacecraft, what other discoveries are still waiting for us within its structural code?